Hi everyone, I'm gonna tell you about the d9d project. The word for distributed, but with 9 letters squeezed. And it's a training framework for large language models. A few words about me. My name is Maxim Afanasyev. I'm the d9d project maintainer. And also I'm a research engineer at Tochka.com. I lead our internal foundation models team, as well as do all these distributed training stuff there. You can find me on LinkedIn, on GitHub, if you want. Yeah. So, agenda of my talk. Firstly, I will introduce those of you who aren't related to distributed training to the distributed training, how it works in general. I won't give you a big lecture about this. I'll try to be short but informative. Then I'll talk about problems, about current tooling for distributed training as I view this stuff. And then I'll talk about the framework itself, how we made them, the highlight APIs. I find the most interesting the project roadmap, and the Q&A, where you can ask me anything. So, why do we need distributed training? That's the first question I'll answer in my 101 section. Then I'll tell you what distributed training regimes are there. There are a lot of them. I want to show you the diversity of them. And then I'll show you how these methods work together actually. So, why do we ever need distributed training? Let's take a Qwen-free 235 billion parameters model, and let's talk about training it in 16 bits precision in a full training scenario. So we either pre-train it or just provide fine-tuning without LoRa adapters. So the model weights alone are just under 500 gigabytes of video memory we need. And if we try to train it, we need also to take into account the gradients, the ADAM states. There are 2 of them. And this way, we need just under 2 terabytes of video memory just to fit the model. So we need at least 22 H100 NVIDIA GPUs. And yeah, it obviously won't even fit into a single GPU. That's reason number 1 why would we need to distribute training. And also, let's take the DeepSeek v3 pre-training scenario. And yeah, let's assume an equal model flops utilization. It's a tough assumption, but it's just to show you the idea. So the DeepSeek guys reported that they were pre-training this model for 2.6 millions of H800 GPU hours. Yeah, H800 is a special NVIDIA GPU for the Chinese market. Yeah, on a small cluster of such 2 GPUs, it would be 10 years to train a model of such scale. And yeah, we obviously can't wait for 10 years. AI is evolving so quickly, so we need to do it faster somehow. Yeah, so we should scale hardware on 1,000 of GPUs. It would be just a bit more than 100 of days to pre-train DeepSeek. And on a large cluster of 16,000 of GPUs, it would be just under 7 days, the pre-training run. So yeah, that's another reason why would we scale GPUs and why would we need distributed training. So in other words, we do distributed training in order to scale both compute and memory to train large enough models in a reasonable amount of time. That's important. Yeah, and now I'll show you the strategies to facilitate the distributed training. So I prefer to group them into 3 categories. First one is about data. It's data parallelism and fully shared data parallelism. Second category is horizontal parallelism. That's how you can split each individual layer onto your GPUs. And the third one is vertical parallelism. That's how you can split the model vertically, layer by layer. So I'll show you some of these methods and describe in a few words how they work. So the simplest distributed training strategy is distributed data parallelism. So basically it works the way you have the same train loop, and it's a bit different from an offline one. So the only difference there is that on multiple GPUs, on different GPUs, you just use different shards of the data set. So for instance, GPU number 1 uses samples from 1 to 1,000, GPU number 2 uses samples from 1,000 to 2,000, and so on. So you share the data. And the second difference is that you synchronize your gradients after a backward pass by using the all-reduced collective communication. That works just the way you have 2 local gradient tensors, you aggregate them, collect them on each GPU, and reduce using the average operation. So you get your global gradient this way. And yeah, it's a pretty a pretty popular method. It works really well for small models, but that's a caveat. For DDP, the model must fit on one GPU, so all the states should fit. So it's perfect for small models, but DDP alone can't make us train DeepSeek v3. Yeah. Another one about the data is FSDP, fully sharded data parallelism. It works just like DDP, but before doing some computations during forward and backward passes, it has each layer sharded across your cluster, across your GPUs. So if you have some linear layers, all of this will be sharded by parts on each GPU. Each GPU will hold only a shard. And before doing any computation, a forward pass or backward pass of some layer, it will gather parts of the model weight matrix onto all the GPUs, do the computation, and reshard it all again. So you can imagine a dog sitting on a train and playing tracks just in front of it, and the tracks before the train are disappearing. So that's FSDP. Yeah. It can scale beyond DDP, so you can fit models that do not fit into one GPU, but it's actually pretty communication heavy. So if you have such a large layer that takes longer to collect than to compute, you will be bottlenecked by FSDP. That's why horizontal parallelism exists, and it could be combined pretty well with DDP or FSDP. An example of horizontal parallelism method is tensor parallelism. So it's a way for sharding your linear layers, but not in the way the model parameters are collected, but in the way the activations are collected. So if your model weights are large, but activations are not, you can use TP. So it can scale beyond FSDP even. And the caveat here is that DDP and FSDP both were model agnostic, so you can use them with anything literally. But TP is model specific. You can use it only with linear layers. You have to put the communications in your model code. And yeah, it's synchronous, so you have to wait for communications to be communicated. You can't do it asynchronously, unlike FSDP. Yeah, that's another one method. So I've told you about splitting the data, about splitting layer, but what about a case when we want to train a model on long context? So if we get 1 million tokens sequences, they will all land on each GPU and obviously won't fit. That's an example, like somebody trying to fit a large sofa onto a small car. Yeah, so we somehow have to split the sequence too. And yeah, before telling you about context parallelism, I want to tell you about the all-troll collective communication. So previous methods heavily relied on all gather. That's just you collect parts of the tensors and concatenate them, and all reduce. That you collect different tensors and sum them, average them. Yeah, all reduce is a bit harder, a bit more complex, but it's really useful for context parallelism and some other parallelism methods. So it works the way that every GPU sends a different piece of data to every other GPU. You can imagine some postmans doing some deliveries here. It's just like a transpose or reshuffle operation across GPUs. And yeah, it's used for one of two context parallelism methods. One of context parallelism methods that's called Ulysses. It's from DeepSpeed, if I remember it correctly. Yeah, and it works the way that, the sequence is split, just like in data parallelism, we split the batch, we split data, we shard it. Now we shard the sequence by the seqlen dimension, and each GPU will know only about a part of the sequence. And this way we can compute all the layers like MLPs, layer norms, embeddings, and so on. But for attention layer, there's some trick. For attention, we do a quick swap using an all-troll operation. So for activations entering the attention layer, we'll have a full hidden state for some part of the tokens, and we'll exchange it to a partial hidden state for all of the tokens. Like we can convert sequence dimension to hidden state dimension. In order to compute attention heads in a distributed way. So if you remember how multi-head attention works, it divides your hidden state into parts, and now you can compute each part of that using different GPUs. Yeah, and then you'll reverse that using another all-to-all operation, and yeah, that's context parallelism. Yeah. So if you can scale context parallelism, for instance, if you have less attention heads than your cardinality for context parallelism dimension, you can use another method that's called ring attention. It's more complex. It works like distributed flash attention. Actually, yeah, you also split the sequence, so each GPU contains only a shard of the full sequence, but you don't do these tricks with hidden states. You just keep the sequence split and change how the scaled report attention operation is computed. Yeah, it is described more preciously in an ultrascale playbook from Hugging Face. It's a great material. So yeah, if you want to know more about ring attention, you can just read ultrascale playbook. It's a great thing from Hugging Face team. Yeah. And the pre-final one, horizontal parallelism method, is also special. So context parallelism was special for attention, and now all the new models are mixture of experts models. And yeah, we have a special parallelism for MOE models too. It's called expert parallelism. Yeah, it works somehow similar to Ulysses context parallelism, that it uses all-to-all communication, but for a different purpose. So for MOE, we have a router that decides for which experts a token should be processed by. And then we have different experts. You can think of them like of a set of different MLP networks. Yeah. So for instance, Qwen3 has 128 experts. Each layer has this amount. Yeah. And each token is processed by some subset of these experts. So it's sparse. And yeah, expert parallelism utilizes this sparsity. So after router has made some decisions, we can run an all-to-all communication to send all the local tokens to all the GPUs that host experts that should compute these tokens. So yeah, it's also useful. It's used heavily nowadays in novel models. Yeah, and that's all about horizontal parallelism. And yeah, let me talk a bit about pipeline parallelism. It's a vertical parallelism method that allows you to cut the model by depth. So you have some model that has some layers, and you just split it by layer from 1 to 8, from 9 to 10, and so on. Yeah, and then you run your execution in micro batches. So for instance, GPU1 hosts pipeline stage 1. It processes micro batch 1, micro batch 2, sends the activations to GPU number 2 that hosts next layers. They process 2, next, and vice versa for the backward pass. The most important thing here is that we have a lot of pipeline bubbles. Yeah, so these are the times where our GPUs are underutilized. So if we can compute anything, we'll have a bubble. Yeah, and there are some novel pipeline parallelism schedules that can tackle with these bubbles. I've shown you the simplest one. It's called gpipe, by the way. Yeah, and it has bubbles, but some schedules don't have bubbles. Yeah, and the most important thing about pipeline parallelism is that it's best for multi-node setups, because sending communications is really cheap. It's not that expensive, for instance, if we compare to sending model weights in FSDP or sending big activations in tensor parallelism. Yeah, pipeline communications are really cheap, and that's why it was heavily used for training GLM5, for instance. They used pipeline parallelism for training DeepSeek. All the really large models utilize pipeline parallelism. Yeah, and why I've told you all this information? That's because I wanted to show you the diversity of distributed training strategies. And yeah, modern models may combine all of them, actually. And the developers training such large models have to think about configuring cardinalities for each of distributed training dimension. Yeah, and it can be pretty tough. Yeah. And also, developers of training frameworks have to think that there actually no like some magical 6D parallel mesh we can map onto real GPUs. Actually, some parallelism methods are special for some layers. For instance, we can apply expert parallelism only on MOE layer. We can apply context parallelism only on attention layer. So yeah, we have actually got different logical grids that map parallelism dimensions onto real GPU hardware. Yeah, that's also important things that the framework developers should care about. Yeah, and actually, the developers utilizing the framework should care about where to sit in that 6D dimensional space. So what train configuration should they use for exactly their own cluster, their own model to get the best model flops utilization. So there are a lot of problems we have to solve. Yeah, and actually, yeah, we can solve these problems with bare PyTorch, but actually nobody does it. We need some tooling for solving this. And now I see the landscape for this tooling that in a way that we have two species actually. First one is monolithic frameworks, and another one is fork and go repositories. About monoliths, there is a great example that's called Megatron LM. It's battle tested and it's really fast. And NVIDIA team did a really good job here. So if you want to train some model using some regime that's supported by Megatron out of the box, it will work. It will work fine. It will work fast. It will train a model for you. But if you want to change anything, for instance, if you are a research laboratory, creating a new parallelism method or a new model that's not supported, obviously, by Megatron LM, you have to find the framework, you have to patch it, and I usually joke that you have to be a PhD in NVIDIA projects to do it properly. Yeah, so it's performant, but it's huge. It's a really major project that could slow your research iteration if you want it to be fast. Yeah, another one is an example of a fork and go repository. It's Torch Titan. It was made by the PyTorch team, and I really like Torch Titan actually, because it gives you full control over every detail. But now every detail is yours to maintain. So if you want to patch Torch Titan, you have to fork it. You have to maintain a distance between your patch for your own local model and the mainstream. So sometimes they may merge it or they may not. So you can just install Torch Titan and compose it a way you want. You have to fork it, modify it, but it works actually for somebody. PyTorch team actually trained Llama using Torch Titan, and they were fine with that. Yeah, and actually I see a gap here. So we have monoliths that are powerful but rigid. We have homebrew setups, fork and go repositories that are flexible but endless. And I actually wanted to use something that's hackable, modifiable, and still fast and still working fine. Yeah, and that's the reason why I thought about building a custom training framework called d9d. And I imagine that the developer experience with d9d should work in this way. So for monoliths, if you want to change something, you'll spend a lot of time. For homebrew setups, you have to fork and patch them and rebase and repeat it a lot. And for another one framework, you can just compose it the way you want and reuse. So that's what I want from a developer experience here. And actually, to make this work, we have pinned some principles before even writing the code. So these principles should be across the whole framework. And these principles actually didn't come from nothing. It came from a real pain points from tools we used, for instance, Megatron and Torch Titan. Yeah. So first principle we've pinned is that d9d should be composable but not monolithic. So the framework still should own the plumbing, but the developer should compose it the way he actually wants. So actually, d9d should be like a box of Lego bricks. So you still don't write your train loop from scratch, but you decide how your loss is computed, how your model is constructed, how it's parallelized across the cluster. And yeah, you should have a set of interfaces you can extend and a set of bricks you can compose. An example of this is how our train configuration works. Train configurator is an object that does all the dependency injection for our trainer object. And what it accepts at construction? It accepts device mesh, your cluster topology, your 6D parallelism setup. It accepts some parameters, for instance, how often we should log our loss in 1 dB, for instance. And yeah, it provides your space for your own interfaces for model provider and task provider. You fully decide how your model works, how your task provider works, how your loss is computed. And also we provide interfaces for optimizing long-range schedule, for instance. But we also have an automatic implementations. If you don't care, you can just use ours. So you can use default optimizers from PyTorch instantiated from PyData configs. Yeah, and also about the data, you can create your fully custom data stack for this, so you can stream different sources onto different data parallelism cardinalities. But yeah, if you don't care, you can use just our auto data provider that will take the whole data set, that will shard it by indices across the data parallelism axis, and yeah, it will just work. So you can either build your own thing or use our bricks. And that's an example how a compute loss function is defined for supervised fine-tuning. So our models, when provided labels, return log probas for target tokens. So you can compute cross entropy, you can compute DPO loss, GRPO loss, and all of them. So yeah, here we just compute cross entropy by summing these log probes and dividing by amount of tokens. And also, an important thing to note is that we support weighting losses. So it's really important for training large language models because in this case, you may have different batches holding different amount of tokens. And if you try to average your gradients across that were produced by losses computed by different amount of tokens, you will actually have these gradients averaged by the same magnitude. But if we weigh this gradient by amount of tokens, we'll take this into an account and average weights using different magnitudes. So there was a lot of problems with this in other projects. Even Onslaught guys posted a blog post on this recently, and it was fixed in Torch Titan in previous November. So yeah, it's an important problem we thought about. So the developer sees loss weighting, and he can take it into account and think, how should I weight my losses in my distributed setup? Another example of composability is that we provide some functions for parallelizing horizontally our models from catalog. But these functions are pretty simple, actually. If you want to create your model with your own distributed training strategy, you can just change these functions. You can utilize some other parallelized functions written by yourself. By the way, all the internal parallelization functions from d9d are written using the modern PyTorch dTensor API. So it's pretty simple. There are some of them for TensorPrint, for instance, in PyTorch. Yeah. And the second principle is that everything should be white box. So the developer should be able to inspect every object in d9d. So model should be a real neural PyTorch.nn.module and know some layer specs that are constructed somewhere else. And there should be no hidden reflection magic, for instance. So the developer should be able to know what is happening under the box. And example of this is actually our train loop. Yeah, we have written the framework the way our train loop actually reads like a train loop. So if you have seen some train loops from PyTorch tutorials, you definitely have seen one. Our train loop reads exactly like this. So we have some another things like gradient clipping, firing even bus events, but actually it's just a train loop that just iterates over the data that computes forward, backward, doing optimization, thinking gradients, and so on. Yeah, so you can read it and understand what's happening under the box. Another example is how we do splitting models for pipelining. Actually, we have an example from Torch Titan on the left-hand side. Yeah, it works, but in my opinion, it's not that transparent as I wanted. So in Torch Titan, it works the way you first construct the whole model, and then in another model, you have it to be split. So it deletes some models, it sets some models to none, it copies your whole model. And if you don't know how exactly Torch Titan works, it could be pretty hard for you to understand what's happening. In d9d, we thought about this and decided that actually each model should be pipeline aware out of the box. actually you can open your model declaration of your model, and to read its init, forward functions, and check what layers are related to first pipeline stage, to last one, to some intermediate stages. So yeah, it happens in one single file, and you don't have to look over the whole code base for it. Yeah, that's how we made it. And the third principle is pretty controversial, but I name it that we wanted d9d to build like real software. Like we usually see a problem that some ML tooling is under-engineered by switching standards. For instance, no strict type checking, leading to type checking errors, no strict linting, and so on. We actually refuse to accept that because now we can use a modern stack for it. And yeah, we used it, and now we have more than 800 of unit tests. There will be more. We have some strict linting rules, some strict type checking from end to end. So the code base is type check from end to end, except for the GPU kernels, actually. And yeah, we have introduced the DEP process. Actually, it's some kind of RFC. You can think it's something like PEP for Python, but DEP for d9d. We made it because we wanted the developers to design each new large feature clearly. So we don't want it to. So we wanted the d9d to become a foundational project, and any design mistake here is expensive. So we introduced RFCs, and we forced developers to write some RFCs before coding, and it also helps AI agents to do implementations better. So you firstly design your DEP with Claude, and then it can implement it in many cases in a few shots. So yeah, also about AI coding, we have pinned some opinionated design principles, and they helped us to write a lot of code using Claude, and it actually now generates a lot less slop than before. So we are fine with it. Yeah, and I've shown you the principles, and now I want to show you the coolest, in my opinion, actually, things, APIs they produced. And first one is distributed context. So in some other distributing frameworks, there are some problems like some frameworks provide you a top-level model that owns the source of truth of your distributed topology. Some of them provide some God object that has distributed topology and a lot of other stuff. In d9d, we wanted to create a small object like that's called distribute context that's created from device mesh parameters, and it's built once and passed explicitly everywhere. You can use it for creating these logical views I've shown you sometime before. So you can use these views for different layers, and yeah, you can trace what's happening from end to end, from creating the distributed context to where it's actually used. And it also contains some utilities for making some distributed aware checks, for setting timeouts for your NCCL process groups. So yeah, you can control your cluster topology from one object, and that's cool in my opinion. Yeah, another one is that how we handle model states. Actually, in training large models, handling states is pretty complex because your model states could easily weigh hundreds and thousands of gigabytes. And for example, we can take a case where we want to convert some model checkpoints that's published on Hugging Face to some format of our internal framework, not Hugging Face transformers. So yeah, we have a large checkpoint, we have a small machine that can fit all the weight. So what can we do? Actually, to solve this problem, we made all the checkpoint processing system a graph processing system, actually. So checkpoints in d9d are graphs. So you can create a graph mapper for it, stating what nodes it should accept and process, what nodes it should output. You can use some mappers that rename some model state keys, that merge some states. There's an example of one that converts separate query count value projection and attention layer into a single one. Yeah, so we made a build system for tensors. You declare targets and dependencies, and it works. And also, yeah, you can do offline checkpoint conversion, a distributed offline checkpoint conversion, actually, because you can create your checkpoint mapper declaratively. You can wrap it into another mapper that will shard all the work across distributed system, across your workers, GPUs or CPUs, either depending on which device you'll convert the checkpoint. And you just run a single method provided by d9d, and that's the way you can convert your checkpoints between different formats. Also, it was a pretty cool use case for parameter-efficient fine-tuning. So if we apply LoRa adapters to a model, we have its weights mapped. So we had in past, for instance, a model named attention, and after applying LoRa, it will be transferred to attention.base. So we wrap it into a LoRa layer of some kind. Yeah, and it's also a case so we can create a model state mapper. We can use it to load the stock model checkpoint on the fly to a new converted model, changed model. And also we can use model state mapping for merging LoRa adapters into base weights and renaming it from attention.base to just attention, for instance. Yeah. Also, I want to talk a bit about kernels and how we use them. Actually, yeah, a great example of where we really need custom GPU kernels is a mixture of experts layer, because if we compute all the experts using a for loop, it will be slow. If we use some out-of-the-box all-toll operations, it will be also slow. So we, for instance, utilized DeepUP project from the DeepSeek guys to do all-toll communication. And we utilized some grouped GAM project from a guy from NVIDIA that computes all the experts in one pass, in one kernel launch, actually. Yeah, and for instance, that's how we handle the kernels. They are not hard-coded. They are not like spread across the whole code base. They are strategy. You can clearly see what kernel is used. And yeah, we took some other kernels from the community. Apart from GPP and grouped GAM, we used Flash Tension 2 and 4 from Mr. 3DAO. We used cut cross entropy from Apple ML team for fused linear layer and cross entropy. And yeah, we don't want to write all the kernels. But sometimes when there's a good project that provides some kernel we need, we can write it for performance needs. So we have written our own RMS norm kernel. By the way, now there's another project by 3DAO we can use instead of our own implementation, but it wasn't in the past, so we have written one. Yeah, we've written our own Swiglu kernels, our own stochastic rounding kernel. Yeah, stochastic rounding is actually a fun thing that allows you to train models in BF16 precision in a more precise way. So yeah, how it works actually. So I personally train a lot of models in BF16 using stochastic optimizers. The difference here is that you can compute your updates for Adam in FP32 precision, and then when you have to cast your FP32 tensors into BF16 precision, you can truncate them, but the result will be biased by rounding. And yeah, to make it unbiased, we can just add a random noise to a number in a FP32 precision and then cast it, and then it will be unbiased. So expectation of rounded FP32 will be the same as a regular FP32 tensor. That's how stochastic rounding works. And yeah, actually, I see that not many people are aware about it, but I'm a big fan of stochastic rounding, by the way. Yeah, and for changing the kernels, for choosing the kernels in cases we have a lot of them, there are some functions that will automatically detect the best kernel you can use based on your hardware and on your needs. So because some attention kernels, for instance, doesn't support some older hardware, some kernels doesn't support attention things that are needed for GPT OSS model, for instance. So yeah, we have small functions for auto detection, so no hidden invariants, so no detection spread across the whole code base. You can read one function and understand what happens here. Yeah, and also I want to show you how our forward-backward execution engine works. So each train loop should actually answer two questions. How long do we train? And what does one step feed the model? And actually, in some train loops I saw, every train loop component answers these questions a bit, each of them. So there are some invariants related to length of a data loader, to some configuration, to some other things. And in d9d, we actually wanted to create a single abstraction that will own all the data stuff. We created a microbatch pack stream. This protocol is implemented already by a stateful data loader from Torch Data package, for instance. So if you don't write your own one, you can just pip install Torch Data and use stateful data loader as a microbatch pack stream. But if you don't want to rely on Torch Data, if you do want to create something custom, you definitely can just use our protocol. Yeah, and it will answer the duration question and the data stream question. Yeah. And also, that's a thing I want to say about how we do gradient accumulation pipelining. So in some other train loops, for instance, in Torch Titan, I saw the guys made different code path for pipelining, a different code path for gradient accumulation, different code path for regular forward and backward. And in my opinion, it was pretty cluttered in a way that you as a developer should read all the code path and understand them. Actually, in d9d, we managed to merge all this path into a single one by creating a little virtual machine that will do all the forwards, backwards, communication for pipelining. And yeah, actually, we took this idea from a torch.pipelining package. So PyTorch guys did a really good work here. So actually, we used the idea, we refactored it a lot, because, for instance, the implementation didn't support paths in arbitrary pytrees in between pipeline stages. We wanted to pass arbitrary pytrees, for instance. So yeah, actually, we created a virtual machine for forwards and backwards. So it's the one VM that runs gradient accumulation, trivial case, and pipelining. And also, we do support so-called zero-bubble pipeline parallelism. That's a thing that allows you to tackle with those nasty bubbles in some slides before. I've shown you those. And yeah, the problem there is zero-bubble pipeline parallelism requires you to do a backward pass in a special way. So you have to separate it in two stages. First stage is backward from outputs to inputs, so they can be sent to previous pipeline stages. And second one is backward from intermediate activations made from the first stage to model weights, so you can optimize. Yeah, and PyTorch actually supports this, but it contains some problems, some bugs, and we have reported them to the team, and they are working on it now. But for now, since these bugs are not fixed, we had to create our own hacks for making ZB, zero-bubble pipeline parallelism work. And I believe someday these problems in PyTorch will be fixed, and yeah, we can remove our own implementation, just use the one from the guys. Yeah, also I want to show you that we support collocated reinforced learning by allowing the developers to put our trainer onto a sleep and wake it. So you can offload all the states from GPU memory to CPU memory, and it will work. So it's also a great demonstration of our event bus system. So actually, you can subscribe to some train events. You can do some work there. For instance, put a trainer onto the sleep, run your rollouts, wake up the trainer, and integrate it with some RL setup, reinforced learning setup. Yeah, and the whole thing actually, if we take a pretend scenario of Qwen3 MOE model, it's not that large. It actually provides all the interfaces, implementations, and it provides all the idea. It even provides a custom data stack. And yeah, it's actually just under 300 of lines. So yeah, it's not a one-liner, definitely. You have to write some code with d9d. But the win here is that you can customize anything, actually. Yeah? And where we run d9d? Actually, we run it at Tochka, and we use it to continually pre-train, not pre-train from scratch, but continually pre-train from original checkpoint Qwen3 model. We use it for mid-training of 235 billion parameters Qwen3 model. Also, I personally use d9d at home for some small-scale classification and post-training on my single GPU, even without a distributed cluster. And that's the same framework for these two different cases. And I really like how it goes, that I can actually write the same code and it will be working on a single GPU, on multiple GPUs, on 1 billion parameters model, on 200 billion parameters model. Yeah, I like it. And actually, yeah, d9d actually started with that. I had a really good end of the previous year. I've created that idea and created the framework, and yeah, it actually now works. In 6 months, we got it working in Tochka, in my own projects, but there are some things to finish before the 1.0 release. Actually, we have to add more models, because now only the Qwen3 MOE is supported. Qwen 3.5 is on the way. And we also have to add all the GLM, Kimi models. Yeah, we have prepared for it. We already support gated data networks, for instance. But yeah, we have to add the models. We'll do it somewhere in this year. We also want to refactor context parallelism, because initially we were using PyTorch 1, but PyTorch do not support flash attention 4. Its context parallelism implementation relied on torch.sdpa prop package. So we actually want to write our own engine utilizing some other context parallelism implementation. We have seen some, for instance, from guys that developed Kimi. Also, tensor parallelism now is unfinished in d9d, not because it's somehow complex to add it, but just because nobody from our team actually utilized it. So we'll still add it, but not now. Yeah, and we want to add some examples beyond supervised fine-tuning, because we want to add examples for classification, for embedding models, for reinforced learning, and so on. Yeah, that's a roadmap of things we want to do before Link 1.0. Yeah, actually, we also are experimenting with our own reinforced learning framework. There are only experiments for now, so don't expect it to be released anyone soon. It may be not even released, even because we still did not confirm that our RL framework is fine. We didn't finish writing it. So yeah, we are working on it. We can ship something, or we cannot. Just saying that we are working on this kind of stuff too. And yeah, you can find the project on GitHub. It's fully open source. It's licensed under Apache 2.0 license. So yeah, you can steer what's happening there. I'll personally advise against using it before 1.0 comes out. But you can check the code, you can contribute, you can run some workloads that are supported for now. And yeah, the team, the core contributors are there. There's Danya, Vlad, me. All these guys made d9d happen. And yeah, thank you all for your attention. You can ask the questions now, I can answer them.
Okay. Thank you very much. If you have questions, microphone will be given to you. First person to raise hand. Yes.
Yeah.
One question per person.
Yeah. Okay. Yeah, I don't know if I asking too much, because yeah, I would really want to involve and try the framework, but I do not have one single H100. But so maybe I'm asking too much. Is there any possibility we can use this framework to do some post-training or reinforcement training upon some very small model?
Yeah, sure. Yeah. I use it on my 3090 GPU, and it works fine for this case. Yeah, I do training embedding models, classification models. Yeah, it will work. Thank you.
Do you have any traceability inside your framework to monitoring efficiency of training? For example, when your trainer is sleep too long and your rollout of and wise exchanging allocate too much time?
Yeah, for the trainer, we do support PyTorch profiler, so we have integrated with it, so you can just enable it in the config and watch the traces using Perfetto. It's a great tool for view profile traces. Yeah, and it will work. And for the reinforced learning, we still haven't finished making out RL framework, so they're not yet. But for the trainer, yeah, you can use Torch profiler.
Thanks. I was wondering if d9d gives some kind of starting points when you have a specific hardware you don't know where to start from. Like, will it kind of help you guide what type of parallelism strategy to choose from, what like hyperparameters or learning rate? Is there something like user guides or maybe like some defaults that you can use?
Yeah, I'd answer that for the introduction into how to configure distributed setups. You can really read the UltraScale playbook from the Hugging Face team. It's great. I really loved how the guys made it. And for the d9d, I plan to make a quick introduction guide for small scale, for mid scale, and for UltraScale, but a bit later when 1.0 comes out. Yeah, thanks for questions.
Thank you for the talk. Just wanted to ask if it is possible to fine-tune an already made model.
I didn't hear.
Fine-tune.
Fine-tune? Yeah, we can use it for fine-tuning. I use it to fine-tune Qwen-free embedding models and Qwen-free classifiers and Qwen-free large language model. Yeah, so yeah, it's suitable for fine-tuning too.
Thank you for the talk. Have you tested your library to see what kind of MFU you get?
Sorry, I can't.
Have you tested the library to see what kind of MFU you get?
Yeah, about the MFUs, we didn't do the benchmarks yet, but we did a lot of exercises with Torch profiler. So we eliminated a lot of CPU, GPU things. For instance, we even have found one in Liger kernel library. That's why we are not using it. But about the MFU, we will benchmark it and report on different cluster sizes and setups when 1.0 comes out. So now we're building the infra and then we'll measure. And yeah, now we just use Torch Profiler to find the big nasty stuff. Thank you.